Linyan May has a Master of Science in Electrical Engineering from KU Leuven in Belgium, where she's currently pursuing a PhD on digital design for embedded machine learning processors in Professor Marian Verhelst's team. And her current research interests include energy-efficient deep neural network accelerators, algorithm hardware co-design optimization, and precision scalable computing. And now she will present for us the talk of ZigZag, an architecture mapping design space exploration framework for deep learning accelerators. Please go ahead and start presenting, Linyan.
Thank you. So today I'm going to present you our work, ZigZag. So it's a deep learning accelerator design space exploration framework, which supports the architecture and the mapping search. So let's start. In the beginning, I will give you a general introduction of the whole, like the background, and then the methodology we use to build the whole framework, and some results according to based on the validation and the experiment, and some extension work that we recently finished, and finally the conclusion. So the introduction part, I will quickly go through the basic concept of the DNN layer, DNN accelerator architecture, DNN mapping, and the co-exploration. So first of all, the DNN layers. Let's take a conv2D layer as an example. So a conv2D layer has a three-dimensional operand space, basically the input, weight, and output, and it can be written into a seven-dimensional nested for loop of MAC operation, as shown here. Each operand has its own irrelevant or relevant loop dimension. So what does it mean? So as shown in the table, each operand for the 7 loop dimension, it can have the relevant loop. So the relevant loop are the loops that defines the dimension of that operand. Like for weight, we have here CK, FX, and FY. For the dimension that do not contribute to the dimension of the operand, we call them irrelevant loop. And those irrelevant loop, they contribute to the data reuse. And for input, since we have this two-dimensional sliding window, so it has some partial relevant loop. So that's the basic concept of. And then a lot of DNN workload can fit into the regular nested for loop format, like listed in the table. Besides conv2D, we have conv1D or depth-wise, point-wise matrix multiplication. They can all be perfectly fit into such a nested for loop format by just putting some not existing dimension to 1. And here I give an example of matrix multiplication, and it can perfectly fit into this format. And this format is very important for our later modeling step. And then the second is the DNN accelerator. So the DNN accelerator, we usually model it as a PE array and the memory hierarchy on top. The memory hierarchy can have whatever level on chip and off chip, from level 1 to the level X. So for each aspect, like from the PE design, the PE array, and the memory hierarchy, it has a large design space individually. Like for the PE design, inside of each PE, some people put one input, like weight input output register. So they do one MAC operation. And within this one MAC operation, there are some variants like the input and the output, like the weight and input register. They can share like one memory, physical memory, and do dynamic memory capacity allocation through different layers. Or some like the weight can be fetched directly from the L1 memory instead of stored locally, or multiple MAC engine can be embedded into one PE. So there are a lot of design options. And then for on top of that, for PE array, the weight input and output, they can have different interconnection pattern. Each one will have a different data reuse distribution between the input and the weight and output. Then on top of that, for the memory hierarchy, we can have a memory sharing between two operands. Like here, I have the input and output sharing at the L2 level. I can bypass the memory hierarchy, memory level in the hierarchy. Like here, I can directly fetch data from the local buffer L2 level to the PE array for weight and input. And here we can also just disable the off chip. We assume if all the data can be stored on chip, then we can ignore the DRAM level. So since there are so many design degrees of freedom in the DNA accelerator design. So we can later, we really need to have a framework to automate the search. And then, so we have discussed the algorithm and then the hardware. From the algorithm to the hardware, we call it mapping, also called it data flow. So the data flow basically has two perspectives. The first perspective is the spatial mapping, basically how to do loop unrolling and map several loops onto the spatially unrolled PE array. And then the second part, the temporal mapping part, how to do loop tiling and ordering to map the rest of the temporal loop onto the memory hierarchy. For the spatial mapping part, we're trying to optimize the operation parallelism. For the temporal mapping part, we're trying to optimize the data locality and the stationarity. Again, it exists a large design space. Note that each of those loops each loop is independent of each other, meaning whatever loop operation trick we do, whatever loop ordering or tiling we do, the algorithm remains correct. So if we do layer-wise operation, that really gives us a large design space for the mapping. So we have discussed these three aspects: the algorithm, the hardware, and the mapping. Besides these three perspectives, we also need to consider the different technologies impact and the new new technologies impact, like the long volatile memory, compute in memory, or 3D integrated circuit. And all the different technology, they will have the impact on the hardware, also have the impact on the mapping. So some other consideration, like what if we have the sparsity in the neural network? What if we have various data precision in the neural network, and also the cross-layer execution patterns? They will all change the optimum point in the design space. So seeing that the huge design space exists at each level and at combined level, we really need to have some framework to automate, to explore the whole large design space. And thanks to the regular workload, the deterministic processing flow, and the well-defined hardware components, we have built such a framework called ZigZag. So now I will introduce you the ZigZag framework, firstly from the overview, and then the three pillars in the framework, which is the unified design point representation, the standardized hardware cost estimation, and the automated design point generation. So the hardware, the ZigZag framework takes in the neural network workload definition. It can be the conv 2D or depth-wise, point-wise, or fully connected neural network dimension size. And it also takes in the hardware constraint that user can put, like what's the area utilization, the precision, and then the memory pool includes a lot of different memory instances that we can use to build different memory hierarchy, and technology dependent cost, like the each MAC cost or interconnection cost. It provides parallel optimal solutions. The optimal accelerator architecture, the optimal spatial and temporal mappings, and the corresponding energy, performance, and area. So inside of the ZigZag framework, we have three different components, which is the architecture generator, the mapping search engine, and the hardware cost estimator. And we will explain the whole framework through these three different perspectives. So firstly is the unified design point representation. How do we model each design point in the framework, which includes all the information from the hardware, from the algorithm, and from the mapping. And secondly, the standardized hardware cost estimation. So given such a unified representation for each dot, how do we estimate hardware cost? And then finally, in order to let it automatically search the design space, how do we automatically generate those design points? So let's start from the first one. So the unified design space representation. We split the whole space into these two dimensions. The firstly is the hardware architecture. So in order to let you see the different settings, I split the hardware architecture with balanced memory hierarchy. Inside this, at all memory levels, we assume that weight, input, and output, they are shared. So basically, every memory level stores all the 3 different operands, or unbalanced memory hierarchy, in which case the memory level and the WIO 3 operands are decoupled. It allows to have for weight, I only have 2 memory level, where for input and output, I can have 3 level. And then on the other dimension, I put the algorithm to hardware mapping. I defined it as even mapping and then the uneven mapping. The even mapping, so let's take an example. Let's look at the example. So here is our one design point example. And here, like the alpha numerical pair inside of each block is like a for loop. So here it means like 4fx from 1 to 5. And then on top of that, I have another for loop for C. So what you see here is that each hardware component, like here, DRAM, global buffer, register file, they have the same mappings. So that's what we call the even mapping. And then for the unbalanced memory hierarchy, the even mapping looks like here. So basically, as long as the memory is shared, the cutting edge between those loop tiling or loop blocking, they are even. And then what it looks like with uneven mapping. So the uneven mapping can do loop tiling, whatever it fits the memory memory capacity. So basically, you can do freely the loop tiling. And then for uneven mapping and unbalanced memory hierarchy, you can do, so it's give a large freedom for the mapping space compared to other such frameworks. So this is the uniform data representation. And just like if you just look at the representation, you already know what's your memory hierarchy. So you know that your weight has 2 levels, your input has 3 levels. You also know what's your total algorithm size, because all the loop dimension size is inside, and also together with the temporal and the spatial information. So now our question is that, given such a representation, how do we estimate the hardware cost in a very standardized way? So we estimate the hardware cost based on the loop relevance principle, which I presented in the first slide. So in this case, based on the relevant or irrelevant loop dimension for each operand, we can extract a set of equations to estimate at each memory level for each operand, what's the data size, what's the total MAC operation it support, and like the key matrix, like what's the memory access count happened at each memory level for read and write. So they can all be extracted following the same procedure, which like a very largely standardized procedure, and allows you to fit in whatever the hardware template you want to try out. So that's our second point. And then the third one is, after we have this standardized hardware cost estimation, we want to automatically generate the design point. And the design point, we define it as the hardware architecture plus the spatial mapping plus the temporal mapping. For each of those different design perspectives, we have developed several search engines or search methods. Like for the hardware architecture part, we have developed a memory pool-based memory hierarchy search engine. So based on the user-defined possible memory candidates, we can automatically generate the memory hierarchy. And then for the spatial and the temporal mapping search engine, we have developed the exhaustive search and the heuristic search, and also iterative search. So here I will not go into the detail, but briefly mention what's the pruning principle that we put at each search engine to reduce the design space. So for the memory hierarchy part, we trying to set a constraint for the size ratio between different memory at different levels in the hierarchy. Also, this ratio can be a size ratio or a cost ratio. And also we trying to let it fit into a certain area. That's the constraint. And then for the spatial mapping, we can analyze the spatial data reuse each spatial mapping scenario provides to input and weight and output. And we can select the parallel optimal ones that to fit into the next temporal mapping search. And then for the temporal mapping part, we can make sure that data reuse exists at each memory level during the loop tiling phase. We can maximize the data stationarity at the lower memory level during loop ordering phase. And there are some other tricks which you can check in our paper for more detail. And note that a lot of more like clever search or optimization algorithms can be applied in this step. So some results. Firstly, the validation. So the validation we did here against the iris published the data on AlexNet. So this is the normalized energy, and the first bar is the model, is the ZigZag model predict one, and then the second bar is the data provided by iris. On the right-hand side, we also validate our model with an in-house accelerator post-synthesis result. And the total energy mismatch across all layers are within 7.5%. And besides that, we also validate our framework with other SOTA framework. Like here, we validate against the time loop and accelergy. So here, what you see that in a group of three, the first two bars are energy validation. So we firstly let the time loop to search for its best mapping, and then we map the best mapping find by time loop in ZigZag and compare the cost. So these two bars shows our cost model really matched pretty well. And then the second, the middle bar and the third bar is the mapping search engine comparison. So basically, then we let the ZigZag find the best mapping that it can find, and then compare with the best mapping that time loop find. And we can see that maximally we can achieve 64% of the memory energy saving. This is because that we can support this uneven mapping. So basically we decoupled the thing that I mentioned before. And then I will show you briefly a case study. So in this case study, what we have done is that we want to compare how the hardware friendly level of different neural network. So here we selected 12 different neural network. And in order to make a fair comparison, we also generated 750 different hardware architecture based on the memory pool that we extracted. And so basically later what you will see is that for each neural network, we run them on this 700 different hardware architecture, and each one can again have thousands or even million level mapping possibility. We take the minimum energy mapping and the minimum latency mapping as the result for each. So basically, yeah. So next slide, you will see this algorithm accuracy, energy, latency, area, design space visualization. So in this slide, you see that for each of these 12 different neural networks, let's just take the NestNet nudge, for example. So you see that it achieves the highest accuracy, which is showed in this color. So top 1 accuracy on ImageNet. And so this is the latency per inference, and this is the energy per inference. And here I also put the area, the chip area. So what you can see is that the NestNet is like a cluster in this region. And I also highlighted the Pareto optimum design point that we find. And each dot represent the hardware, a different hardware architecture among that 750 different architecture. And you can really see the trends that if you go to like more and more accurate, like that means also you have more parameter, you have a deeper neural network, you achieve better accuracy, but at the same time you lose the latency and energy, like magnitude order of magnitude. And then we find that the best one is the mobile V3. Yeah, so it's like just to show how powerful such a framework can bring you. And there are more details I will skip for now. So last part is the two extension that we have made based on such a framework. So firstly is the in-memory computing modeling using ZigZag. And here we compare the two different cores. And we also tried to see how the design space varies between these two different scenarios. And then also on the other hand, we are improving the different search engines. So here we also published a work named NOMA, which is a fast exhaustive temporal mapping search method. and it can bring a lot of speed up on top of our previous one. So I won't go into detail, but I will put the link in the end. So the conclusion and the key takeaway, the high-level design space exploration is important to gain insight from the vast joint DNN hardware mapping design space. And a general 3-step methodology for building such a DNN accelerator design space exploration framework is that firstly, you need to unify the data representation to try to cover all the information, and then standardize the cost extraction based on such a representation. And then the third step is to automate the design point generation. Finally, the ZigZag, we can find as such a framework, we can find better design point due to its uneven mapping support. And it can be applied, extended, improved in multiple directions, and we are working on it. So thank you for your attention. And we have open sourced our framework in the GitHub, and we are keep improving it. So any question is welcome.
Thanks a lot, Linyan. That was really interesting. I would say, particularly maybe for something like me, who's actually working with this kind of design exploration myself. So really, really interesting. So
thank you.
We do actually have one for a question from a panelist here.
Yeah.
It's from Paul Deter. He's wondering on slide 16, is the energy there per inference? Yes.
This is the energy for running one convolutional layer.
Okay.
Yeah.
Thank you. So then also I have a question here. So I'm just wondering for the power consumption, when you distribute the workloads on the PEs, do you take into account if the inputs are stable between different jobs? So sort of, does it take into account whether inputs are changing between different workloads, sort of different schedulings?
You mean the data pattern inside of each?
Yes, sort of if you prioritize schemes that keep input stable as to keep power consumption down, if you have similar, or if you think that would have any value or relevance to your work.
Yeah, so we took into account the different operands like the input weight or output stable or stationarity when we do the temporal mapping search. So we can generate all the stationarity scenario, and then we will compare which stationarity is the optimal, and we will take that one as the temporal mapping, if that's what's in.
Yeah, excellent. Thank you.
Thank you.
Yes, I think we'll stop there. And for all the attendees, please use the Q&A. Well, actually, there is another question. Let's pull that in as well. So, any idea or how or if such frameworks could be extended for RNNs? Thanks for the presentation. From Musa Nasir.
Thank you. That's a very nice question indeed. So the major difference, or let's say in it this way. So right now the framework does all the exploration layer wise. So no matter it's RNN or CNN, what we take in as the workload is each layer's dimension. And right now we don't care about the connection between different layers. So basically, if you give me an RNN, I just take all the layer dimension and then just to estimate the cost for each layer separately and then add them together. That's also what we are now trying to also input the layer connection information inside and to see if there is cross-layer data reuse possibility. So right now we only consider within one layer what's the data reuse possibility and trying to optimize for that. But that's our next step. So yeah, for RNN, we will have a different layer connection. That's later, yeah.
Okay, I can see there are actually other questions as well, but I think in the conscious of time, I think we'll stop there and we'll make sure we forward those questions to you, Linyan. I actually have more myself.
I will reply. I will reply.
And you can reply later. Yeah.
Yes.
Thanks a lot, Linyan.
Thank you.
Of course, I do want to thank all our sponsors. So the premier sponsor, Newton, with their automated TinyML solutions. Executive sponsors, ARM, and we organized also a very nice panel that we witnessed just now. Edge Impulse as well. Jan was there and presented some of their work just now as well. Then also Qualcomm, working on advancing AI research to make efficient AI ubiquitous. Sentient, working on chip solutions to do ultra-low power, high-performance deep neural network processors. Then our platinum sponsors, Infineon, we've had a keynote from Wolfgang from Infineon earlier today. Reality AI, working on advanced sensing with Edge AI and TinyML. Then our gold sponsors, Latent AI, working on adaptive AI for the intelligent edge. SensiML, building smart IoT sensor devices from data. And then our silver sponsors, EMSA, where Ilat also presented today what they are up to, Green Waves Technologies, HOTG, Imagimop, Kiso, SEED, and ST. And with that, that's the wrap for today. Thank you everyone for your attention and your attendance.